Last time we talked about what vertical asymptotes are. Now we're going to talk about how you actually get them. What kind of functions tend to have vertical asymptotes? Now the main way that you get vertical asymptotes, it's not the only way, but it's the main way, is by ratios where the denominator goes to 0. So if you have a ratio f of x over g of x, and the denominator goes to 0, and the numerator doesn't, then you're going to get a vertical asymptote. Because if you pick a number that's very close to a, f of x is not going to be close to 0. G of x is going to be close to 0. And what happens when you take a reasonably sized number and divide it by a tiny number? You get a gigantic number. So as an example, let's look at the function f of x is equal to x squared plus 1 divided by x squared minus 1. So the numerator never goes to 0. The numerator is always at least 1. Never goes to 0. But x squared minus 1 goes to 0 at x equals plus or minus 1. So if we make a graph of this, we should expect to have a vertical asymptote at x equals 1 and another vertical asymptote at x equals minus 1. So let's look carefully at how the function behaves near these asymptotes. If x is slightly bigger than 1, then x squared plus 1 is positive. X squared minus 1 is positive. So the ratio is positive, but it's very big because the denominator is tiny. So when x is slightly bigger than 1, the function goes off to plus infinity. When x is slightly less than 1, this is positive, but this is negative. 0.9999 squared is a little less than 1. Subtract 1, you get something negative. And take positive divided by negative, and you get something very negative. The same thing happens at the other end. If x is slightly less than negative 1, this is positive, and you go off to infinity. If you're slightly less than negative 1, slightly bigger than negative 1, you go off to minus infinity. In fact, the curve winds up looking like this. Vertical asymptotes at 1 and minus 1, because that's where the denominator goes to 0 and the numerator doesn't. And you have to check what's happening to the right, what's happening to the left of each asymptote to see whether you go up or down. Okay. Now let's look at a function where the numerator and the denominator both go to 0 at a certain place. Let's look at the function. We look at the function x squared minus 3x plus 2 divided by x squared minus 4. Now, the denominator goes to 0 at plus or minus 2. So you might think that you have a vertical asymptote at 2 and one at minus 2. But the numerator goes to 0 at x equals 1 and x equals 2. So if you draw the curve, you know something funny is going to happen at x equals minus 2. At x equals minus 2, the denominator blows up. The denominator goes to 0, the numerator doesn't, the thing's going to blow up. You wonder, are you going to have something happening at x plus 2? In fact, you don't. In fact, well, let's look at what happens near minus 2. If you're slightly less than minus 2, this is negative, and this is positive, so you go off to minus infinity. Sorry, scratch that. They're both positive. It goes off to plus infinity. If you're slightly bigger than negative 2, this is negative, and this is positive, and it goes off to minus infinity. But then, it doesn't go off, do anything funny here at all. And the reason is that x squared minus 3x plus 2 is x minus 1 times x minus 2. X squared minus 4 is x plus 2 times x minus 2, and the x minus 2's cancel. Really, we're talking about a function, the numerator and the denominator goes to 0 at the same rate, and when you cancel that, you get something that is not doing anything funny at x equals 2, not doing anything funny at x equals 2, so the ratio doesn't do anything funny at x equals 2. It's got a perfectly nice limit, and so the entire curve, I drew it badly, but the entire curve has a hole there. The function isn't defined because it's 0 over 0, but the limit is perfectly nice, and the limit over here is there. So you've got a vertical asymptote at x equals negative 2, not at x equals plus 2. In general, if you have a situation that looks like 0 over 0, it's complicated. You have to do more work to figure out what's going on.